252 million years ago, the Earth was dying. Not from a meteor, not from an explosion, from volcanoes. Thousands of volcanoes erupting simultaneously for approximately 1 million years in the region now called Siberia. They released enough carbon dioxide into the atmosphere to raise ocean temperatures by 10 degrees Celsius, or 18 degrees Fahrenheit. They released enough chlorine to destroy the ozone layer completely. They released enough mercury that traces of it are still found today in rocks on the opposite side of the planet, in South Africa and in Australia. 96% of all marine species disappeared. 78% of all land vertebrates disappeared. This was not simply an extinction. It was the near complete erasure and reboot of life on Earth. And from that ash, eventually came the dinosaurs, and the mammals, and you. Before we go any further, please subscribe to this channel. Your support really helps us to continue our work. Thank you. There is a hierarchy of catastrophes in the history of life on Earth, and most people know the wrong one at the top. When the average person thinks about mass extinction, they think about the asteroid that struck the Yucatan Peninsula 66 million years ago and killed the non-avian dinosaurs. That event, the Cretaceous-Paleogene extinction, was genuinely catastrophic. It eliminated approximately 3/4 of all species on Earth. It ended the reign of the most spectacular large animals the planet had ever produced. Its geological signature is sharp, clean, and global. A thin layer of iridium-rich clay found in rock sequences on every continent. The chemical fingerprint of an extraterrestrial impactor that delivered more energy to the Earth's surface in the first few seconds of its impact than all the nuclear weapons ever built would release, if detonated simultaneously. But the Cretaceous-Paleogene extinction was not the largest. It was not the most severe. It was not the closest the biosphere has ever come to total collapse. That distinction belongs to an event that happened 186 million years earlier, at the boundary between the Permian and Triassic periods, 252 million years ago. An event with no single dramatic moment, no iridium layer, no asteroid. An event caused by processes so familiar that their modern analogues are subjects of active political debate. An event so severe that paleontologists call it, without hyperbole, the Great Dying. The numbers that define the Great Dying are almost impossible to absorb on first encounter. 96% of marine species, 70% of terrestrial species. The trilobites, the iconic arthropods that had dominated ocean floors for 270 million years, that had survived every previous extinction event in the history of complex animal life, that had diversified into more than 20,000 known species, gone, completely and finally, never to return. The rugose and tabulate corals, the organisms that had built the great reef systems of the Paleozoic Ocean, gone. More than half of all marine invertebrate families, gone. The biodiversity of the ocean, which had been building steadily for 300 million years since the Cambrian explosion, reduced to perhaps 4% of its pre-extinction value. On land, The picture was, in some respects, even more stark. The Permian period had been, for land vertebrates, a time of extraordinary evolutionary radiation. The dominant animals on the Permian land surface were not reptiles in the sense we normally think of the word. They were synapsids, the lineage that would eventually give rise to mammals, but that in the Permian had diversified into an extraordinary range of body plans and ecological roles. There were the dicynodonts, the most successful and diverse of the Permian land vertebrates. Herbivores that ranged in size from rabbit to hippopotamus, and that occupied the ecological roles now filled by everything from rabbits to elephants. There were the gorgonopsids, the apex predators of the late Permian, wolf to bear-sized carnivores with long saber teeth, fast-running hunters that had no equivalent in any subsequent ecosystem. There were the dinocephalians, massive herbivores and carnivores that dominated the middle Permian. And there were the cynodonts, small insectivorous synapsids, whose descendants would eventually, after the extinction, give rise to every mammal that has ever lived. All of these lineages were devastated. Some were eliminated entirely. The gorgonopsids, every last one, were gone by the time the Permian-Triassic boundary had been crossed. The dinocephalians, gone. Even the enormously successful dicynodonts, which had been the most diverse large land vertebrates in Earth's history, were reduced to a single surviving genus. The new research published by Brown University and the University of Utah, presented in the Proceedings of the Royal Society B, analyzed nearly 8,600 fossil specimens from the southern Ural Mountains of Russia and the Karoo Basin of South Africa, and concluded that approximately 78% of all land-based vertebrate genera perished in the end Permian mass extinction, a figure significantly higher than many previous estimates had suggested. The scale is not a statistic, it is an emptying. Understanding why this happened requires understanding both the world that was lost and the mechanism that destroyed it. The Permian world was radically different from the one we inhabit. All of the continents were assembled into a single landmass, the supercontinent Pangaea, surrounded by a single global ocean called Panthalassa. The geography of Pangaea created climatic extremes that no modern continent can match. The interior of Pangaea, far from any moderating oceanic influence, experienced seasonal temperature swings of extraordinary magnitude, summer heat that would be lethal to most modern organisms, winter cold that drove continental-scale glaciation. The coastlines of Pangaea, by contrast, were influenced by the warm Tethys Sea that penetrated into the eastern margin of the supercontinent, creating environments of high biological productivity and diversity. The oceans of the Permian world were among the most biologically diverse that have ever existed. The great reef systems of the Permian were built not by the scleractinian corals that construct modern reefs, but by a different group, the rugose and tabulate corals, alongside calcareous sponges called archaeocyathans, and vast communities of brachiopods, bryozoans, crinoids, and ammonoids. These reefs were extraordinarily complex three-dimensional structures that supported thousands of associated species. The biological equivalent of the modern coral triangle of the Indo-Pacific, but extended across a much larger portion of the global ocean. In the deeper waters, trilobites still crawled across muddy seafloors, representatives of a lineage that had already survived 4 previous mass extinction events, spanning 270 million years of geological history. The late Permian land surface, for all its climatic extremes, was covered in vegetation. Vast conifer forests in the higher latitudes, seed fern forests and horsetail swamps at lower latitudes, a complex mosaic of plant communities that supported the diverse vertebrate fauna we have described. The Gondwana landmass, the southern portion of Pangaea that comprised what is now Africa, South America, Australia, India, and Antarctica, was covered in the Glossopteris flora, a distinctive assemblage of seed ferns whose fossilized leaves are found on every southern continent. One of the most compelling early pieces of evidence for continental drift. This was a world of high biological complexity, high diversity, and extraordinary evolutionary achievement. A world that had been building its biological riches for 300 million years since the Cambrian explosion. The specific organisms of the late Permian Ocean deserve individual portraits, because the statistics of their loss, 96% of marine species, obscure the biological reality of what was actually eliminated. The trilobites alone represent a loss of staggering magnitude. By the late Permian, trilobites had already been declining for tens of millions of years, from their Ordovician and Silurian peaks, when they had dominated the ocean floor in extraordinary diversity. But they were still present, still diversified into dozens of species in the late Permian, still one of the defining animals of the Paleozoic ocean floor. They had survived the late Ordovician mass extinction, the late Devonian mass extinction, the end Guadalupian extinction event of the Middle Permian. They had been crawling across seafloors for 270 million years when the Siberian traps began to erupt. And then they were gone, completely, finally, without a single surviving lineage. The trilobite body plan, which had proved adaptable to an extraordinary range of ecological conditions across 270 million years, was simply incompatible with the conditions of the early Triassic Ocean. The blastoids, a group of echinoderms related to sea urchins and sea stars, were equally definitively eliminated. The blastoids had been an important component of Paleozoic reef and seafloor communities, their flower-like feeding arms filtering organic particles from the water column. They were not particularly diverse by the late Permian, but they were present, and then they were not. The Fusulinid foraminifera, single-celled organisms that built elaborate calcium carbonate shells of extraordinary complexity and beauty, some growing to the size of a grain of rice in an organism consisting of a single cell, were eliminated. The tabulate corals, which had built reef frameworks since the Silurian, were eliminated. The rugose corals, which had independently evolved the reef-building strategy and diversified into thousands of species, were eliminated. Every single one of these groups, lineages that had survived for hundreds of millions of years, was terminated at the Permian-Triassic boundary. The brachiopods, The shell-bearing filter feeders that had been the dominant sessile invertebrate of the Paleozoic ocean were devastated, but not quite eliminated. They survive today, represented by approximately 300 species, a ghost of the thousands of species that had inhabited the Permian Ocean. Walk into any natural history museum in the world, and you will see display cases full of Paleozoic marine invertebrate fossils, the vast majority of which are brachiopods. Those museum collections are archives of a biological world that the great dying unmade. The modern ocean, with its bivalve-dominated benthos and its scleractinian coral reefs, is a rebuilt world, different from the Paleozoic world, not inferior in complexity, but profoundly different in character, its organisms the descendants of the survivors, and the opportunists rather than the heirs of the dominant Paleozoic lineages. And then Siberia began to erupt. The Siberian traps. The name comes from the Swedish word for stairs, trap, referring to the stepped topography created by the stacked lava flows, represent one of the largest volcanic events in the history of the solar system within the context of terrestrial continental volcanism. Approximately 252 million years ago, a massive mantle plume impacted the base of the Siberian continental crust, producing a volcanic episode that ultimately covered an area of approximately 3 million square kilometers, roughly the size of the continental United States, in basaltic lava and related intrusive rocks. The total volume of volcanic material produced has been estimated at between 1 and 4 million cubic kilometers. For context, the largest single volcanic eruption in recorded human history, the Tambora eruption of 1815, produced approximately 160 cubic kilometers of material. The Siberian traps produced somewhere between 6,000 and 25,000 times as much. But the raw volume of lava, enormous as it is not the primary reason the Siberian traps caused the end Permian extinction. Basaltic lava flowing across the surface of Siberia, however vast the quantity, would not by itself have been sufficient to trigger a global biological catastrophe of the observed magnitude. The critical factor was not what the Siberian traps erupted onto the surface, but what they injected into the atmosphere, and crucially, the geological context through which those magmas were emplaced. The research published in Annual Reviews of Earth and Planetary Sciences in 2025, reviewing the anatomy and lethality of the Siberian traps, emphasizes a point that has become increasingly clear from the accumulation of high-resolution geochemical data. The most destructive phase of the Siberian traps was not the surface lava flows, but the sill intrusions, magma forced horizontally through the surrounding sedimentary rocks at depth rather than erupting at the surface. And the sedimentary rocks of the Siberian basin through which those sills intruded were not ordinary rock. They were coal beds and evaporite deposits, sequences of organic carbon and evaporated marine salts that, when heated by intruding magma, released enormous quantities of greenhouse gases, halogen compounds, and toxic chemicals directly into the atmosphere. The process is called contact metamorphism. When a hot magma body intrudes into coal or organic-rich sediment, it heats the surrounding rock to temperatures sufficient to volatilize its organic content without actually burning it. The result is the production of vast quantities of methane and carbon dioxide from the coal, and vast quantities of chlorine, fluorine, sulfur dioxide, and other halogens from the evaporites. These gases were not released from volcanic vents that could be located and mapped. They were released from thousands of contact aureoles distributed across the entire extent of the intrusive complex. A diffuse, pervasive, almost impossible to quantify source of atmospheric contamination that dwarfed the direct volcanic emissions from the surface lavas. The global reach of the Siberian Trap's atmospheric contamination has been confirmed by the mercury proxy records discovered in rock sequences on the opposite side of Pangaea. Mercury is a trace element naturally associated with volcanic activity, and elevated mercury concentrations in sedimentary rocks are widely used as a proxy for nearby or distant volcanic input. The research published in Nature Communications, involving scientists from China, South Africa, the United States, and the United Kingdom, demonstrated that mercury anomalies at the Permian Triassic boundary are found not just in rocks close to the Siberian eruptions, but in the Karoo Basin of South Africa and the Sydney Basin of Australia, locations that were in the southern hemisphere, nearly antipodal to the Siberian eruptions. The positive delta 199 mercury values in these southern hemisphere records indicate that the mercury was atmospherically transported, having traveled the entire circumference of the Earth before being deposited in the sediments that are now exposed at the surface in South Africa and Australia. The Siberian traps reached everywhere. The geological detective work that established the Siberian traps as the cause of the end Permian extinction has been one of the most sustained and technically demanding research programs in the history of geology, spanning more than 3 decades and involving researchers from dozens of countries working on rock sequences on every continent. The causal connection is now supported by multiple independent lines of evidence that converge on the same conclusion with a consistency that has persuaded the geological community to a degree of consensus rarely achieved on questions of such complexity. The most fundamental line of evidence is the temporal coincidence between the Siberian Trap's magmatism and the extinction event. The high-precision uranium-lead dating of zircon crystals from volcanic ash layers in both the Siberian Traps sequence and in marine sedimentary sequences containing the extinction horizon has established that the two events are contemporaneous to within the uncertainty of the dating methods, approximately 10,000 to 50,000 years. This temporal coincidence does not prove causation, but it is the necessary starting point for any causal argument. The second line of evidence is the geochemical fingerprint of the volcanic emissions in the extinction boundary sediments. The elevated mercury concentrations at the Permian Triassic boundary, which have now been documented at dozens of sites across the globe, from the Canadian Arctic to South Africa to China to Australia, carry isotopic signatures that specifically indicate atmospheric transport of volcanic mercury rather than local weathering sources. The nickel isotope ratios in Canadian high Arctic boundary sediments, with their extraordinarily light isotopic compositions, that can only be explained by nickel-rich aerosol particles from the Siberian volcanic terrain, provide a specific chemical fingerprint of Siberian traps material in distant marine sediments. The sulfur isotope anomalies, the carbon isotope excursions, the strontium isotope shifts. Each of these geochemical signals in the boundary sediments is consistent with the specific chemical composition of Siberian traps emissions and inconsistent with any other proposed cause. The third line of evidence is the biological selectivity of the extinction. As Andrew Knoll and his colleagues have demonstrated in a series of papers that have become foundational to the field, the pattern of survival and extinction among marine invertebrates is not random with respect to physiology. The organisms with the greatest physiological buffering capacity, active respirers, organisms with internal carbonate chemistry control, mobile organisms capable of moving to better conditions, survived at significantly higher rates than organisms with passive respiration, rigid dependence on external seawater chemistry for calcification, and sessile lifestyles. This non-random pattern is the biological signature of the specific kill mechanisms proposed for the Siberian traps: elevated CO2, ocean acidification, thermal stress, and anoxia. And it constitutes a strong independent argument that those mechanisms were actually operating. The cascade of environmental consequences that followed the initiation of the Siberian traps eruptions was not a single kill mechanism, but a suite of simultaneous and synergistic assaults on the chemistry of the atmosphere and ocean that attacked life through multiple pathways simultaneously. Understanding this cascade requires following the chain of chemical consequences from the volcanic source through the atmosphere and ocean to the organisms that bore the biological cost. The first and most fundamental effect was global warming. The CO2 and methane released by the Siberian traps and the associated contact metamorphism enhanced the greenhouse effect on a massive scale. Current estimates of the carbon release from the Siberian traps range from approximately 10,000 to 40,000 gigatons of carbon, compared to the approximately 9.5 gigatons per year currently being released by human fossil fuel combustion. The rate of release was far slower than modern industrial emissions on a per-year basis, but it operated over hundreds of thousands of years, accumulating in the atmosphere and ocean system faster than the geological processes that remove carbon dioxide from the atmosphere through silicate weathering could compensate. The result was a rise in global mean surface temperature, estimated at between 5 and 10 degrees Celsius above the already warm Permian baseline, a warming event that pushed equatorial sea surface temperatures to approximately 40 degrees Celsius, or 104 degrees Fahrenheit, in the low-latitude Tethys Sea. At these temperatures, most marine organisms that had evolved in cooler conditions were physiologically stressed beyond their capacity for thermal adaptation. The second mechanism was ocean acidification. The same CO2 that was warming the atmosphere was dissolving in the ocean, forming carbonic acid and lowering the pH of seawater. The organisms most vulnerable to ocean acidification are those that build their skeletons and shells from calcium carbonate, which describes almost every major group of marine invertebrate in the Permian Ocean. Corals, brachiopods, bryozoans, echinoderms, mollusks, and the calcareous plankton that form the base of the ocean's food web all depend on their ability to precipitate calcium carbonate, and this ability is severely impaired when ocean pH drops below certain thresholds. The coral reefs of the Permian Ocean, some of the most biologically complex structures in the history of life, were chemically dissolved from beneath as the ocean acidified around them. The third mechanism, and ocean anoxia, the depletion of dissolved oxygen from seawater. Warm water holds less dissolved oxygen than cold water, so the temperature increase directly reduced the ocean's oxygen carrying capacity. Simultaneously, the enhanced input of nutrients from continental weathering in the hotter, more chemically aggressive atmosphere drove algal blooms whose decomposition consumed oxygen in the water column. The result was the expansion of oxygen minimum zones into areas of the ocean that had previously been well oxygenated, and in the most severe cases, the complete deoxygenation of entire ocean basins. Organisms that had evolved in well-oxygenated water found themselves suffocating in water from which the oxygen had been removed. The combination of thermal stress, chemical stress, and oxygen deprivation created conditions that were simultaneously lethal through multiple independent pathways. The fourth mechanism was ozone layer destruction. The halogen compounds, chlorine, fluorine, bromine, released by the contact metamorphism of the Siberian evaporites, were chemically capable of destroying stratospheric ozone through the same catalytic cycle that modern chlorofluorocarbons exploit in the modern ozone hole. The estimated halogen release from the Siberian traps has been calculated at quantities sufficient to severely deplete or entirely destroy the stratospheric ozone layer, exposing the surface of the Earth to levels of ultraviolet radiation that would have been lethal or severely damaging to land organisms and shallow marine organisms. The biological evidence for elevated UV radiation at the Permian-Triassic boundary includes the discovery of malformed and mutated pollen and spores in rock sequences from across Pangaea, the biological equivalent of radiation damage preserved in the fossil record. Plants exposed to elevated UV produce abnormal spores with distorted morphology, and these malformed spores are found in abundance in Permian-Triassic boundary sediments from multiple continents. The fifth mechanism was the release of toxic metals. The volcanic emissions of the Siberian traps included not just carbon compounds and halogens, but a range of trace metals: nickel, arsenic, lead, cadmium, at concentrations that were highly toxic to marine organisms. Research published in Nature Communications demonstrated that the lightest nickel isotope ratios ever measured in sedimentary rocks are found in Permian-Triassic boundary deposits in the Canadian High Arctic, evidence of nickel-rich aerosol particles from the Siberian traps being transported globally and deposited in the ocean, where they dramatically altered the chemistry of seawater and disrupted the biochemistry of marine organisms that had never encountered metal concentrations at those levels. The sixth mechanism, and one of the most recently recognized as significant, was volcanic winter. The sulfur dioxide emissions from the Siberian traps were intermittent rather than continuous, reflecting the episodic character of the volcanic activity. Large sulfur dioxide emissions produce sulfate aerosols in the stratosphere that reflect incoming solar radiation back into space, causing short-term surface cooling. The interaction between the long-term warming driven by CO2 and the short-term cooling pulses driven by SO2 episodes created a climate system characterized by extreme instability, oscillating between periods of intense heat and short cold intervals, preventing the establishment of stable environmental conditions under which stressed populations could begin to recover. The ecological stress of this instability may have been as damaging as any single extreme condition. The question of whether the end Permian extinction occurred in a single pulse or in multiple pulses has been debated for decades and is still not fully resolved. The Maishan section and other high-resolution boundary sequences show evidence of a stepped pattern of extinction, a preliminary episode of extinction beginning somewhat before the main pulse, followed by the catastrophic main extinction event, followed by secondary extinctions in the early Triassic as the environmental deterioration continued. Some researchers have argued for 2 or 3 discrete extinction pulses, each corresponding to a specific episode of Siberian traps activity. Others argue that the apparent multipulse structure is an artifact of sampling, that the rock record is not continuous enough to distinguish between a single rapid extinction and multiple closely spaced extinctions. The most sophisticated recent analysis, using the high-resolution geochronology from multiple boundary sections combined with detailed statistical modeling of the fossil record, suggests that the main marine extinction was indeed, essentially, a single event of approximately 60,000 years duration, geologically instantaneous, but that it was preceded by an extended period of biological stress that reduced diversity and made the final extinction pulse more catastrophic in its effects. A healthy, diverse ecosystem with large population sizes and high redundancy in ecological functions is more resistant to perturbation than a stressed, simplified ecosystem already operating near its resilience limits. The preliminary stress phase of the extinction, driven by the early Siberian traps emissions before the main magmatic pulse, may have reduced the resilience of the Permian ecosystem to the point where the main pulse was able to produce a collapse that would not have been possible if the biosphere had been at full biological health. This staged structure, preliminary stress followed by catastrophic collapse, has an uncomfortable resonance with the modern situation. The biological communities of the modern ocean are already stressed by warming temperatures, ocean acidification, overfishing, pollution, and habitat destruction. The resilience that healthy ecosystems provide against further perturbation has already been substantially reduced in many parts of the world. The end Permian event reminds us that once a biological system has been pushed to a sufficiently degraded state, the threshold for irreversible collapse can be much lower than the threshold for initial stress. The Permian biosphere did not collapse because it was suddenly overwhelmed by a perfectly healthy ecosystem. It collapsed because a preliminary phase of stress reduced its capacity to resist, and then a catastrophic pulse pushed it past the point of recovery. The difference between the end Permian extinction and the modern situation is one of rate and agency rather than mechanism. The Siberian traps were not intentional. The geological processes that produced them were indifferent to their biological consequences. The modern carbon release is the product of choices. Choices made by billions of individual actors organized into economic and political systems, operating under constraints that include but are not limited to their awareness of the geological record. The geological record of the Great Dying is not a prediction. It is a data point, the most extreme data point available, in the empirical study of what happens to biological systems when carbon dioxide is released rapidly and in large quantities into the atmosphere. What scientists and policymakers do with that data point is a question of human agency that geology itself cannot answer. The seventh mechanism was hypercapnia, the direct physiological effect of elevated carbon dioxide concentrations on the metabolism of organisms. Andrew Knoll of Harvard and his colleagues have argued that the selectivity of the end Permian marine extinction, the fact that organisms with active respiratory physiology survived at much higher rates than those with passive respiratory physiology, is best explained by the direct toxicity of elevated CO2 to organisms whose metabolic systems could not compensate for changes in blood pH caused by CO2 dissolving in body fluids. Organisms with simple respiratory systems, brachiopods, bryozoans, rugose corals, were devastated. Organisms with active respiratory physiology capable of compensating for hypercapnia, fish, some arthropods, survived at much higher rates. The extinction was not random. It was filtered through physiology, selecting against precisely the organisms that had been most successful in the Permian Ocean. These 7 mechanisms did not operate sequentially. They operated simultaneously, with each reinforcing and amplifying the others. An organism already stressed by thermal warming was less capable of buffering the effects of ocean acidification. An organism already weakened by hypercapnia was less capable of avoiding the expanding anoxic zones. A reef system already dissolving in acidified water had no capacity to resist the additional damage from UV radiation. The synergy between the mechanisms produced a kill efficiency that no single mechanism could have achieved independently. The timing of the extinction, how fast it happened, and whether it was a single event or a series of pulses, has been one of the most actively debated questions in Permian Triassic research. The most precise radiometric dating of Permian Triassic boundary sequences, using uranium-lead dating of zircon crystals in volcanic ash layers, intercalated with the fossiliferous sediments, indicates that the main pulse of marine extinction occurred over a geologically very brief interval, approximately 60,000 years in duration. 60,000 years is a long time by human standards, but in geological terms it is essentially instantaneous. A thin line in the rock record that separates the biologically rich Permian below from the near biological desert of the earliest Triassic above. But the situation on land was more complex, and the new research published in 2025 has dramatically clarified and in some ways complicated the picture of the terrestrial extinction. The research from Brown University and the University of Utah, and the complementary work on the Karoo Basin sediments, dated using uranium-lead zircon geochronology, has established that the terrestrial extinction began hundreds of thousands of years before the marine extinction pulse. The base of the Lystrosaurus assemblage zone in the Karoo Basin, the stratigraphic level at which the characteristic post-extinction disaster fauna first appears, predates the marine Permian Triassic boundary by several 100,000 years. The land started dying before the ocean. The implications of this temporal offset between terrestrial and marine extinction are still being worked out by researchers, and the debate is one of the most active in Permian Triassic research. If the land started dying first, it suggests that the initial kill mechanisms were primarily atmospheric rather than oceanic. Acid rain, ozone depletion, climate instability, and direct temperature stress affecting land organisms before the full cascade of oceanic consequences had developed. This makes sense in physical terms. The atmosphere is where volcanic gases arrive first, and land organisms are directly exposed to atmospheric chemistry in a way that marine organisms, buffered by the thermal and chemical mass of the ocean, are not. The uranium-lead dating of zircon crystals from volcanic ash layers in the Karoo Basin, conducted by an international team including researchers from the University of California, Berkeley, and the University of Connecticut, established that the base of the Lystrosaurus zone in the Karoo predates the marine extinction horizon by several 100,000 years. A difference that is small in absolute terms but geologically significant. The land was already transitioning to its disaster fauna, while the marine extinction was still building toward its catastrophic peak. The organisms of the Permian land surface were, in a very real sense, the canaries in the geological coal mine, the first to show the lethal effects of the environmental deterioration that would soon consume the ocean as well. This temporal offset also helps explain a puzzle in the terrestrial fossil record that had previously been difficult to interpret. The Karoo Basin contains a sequence of fossil-bearing formations that spans the Permian Triassic transition in unusually complete stratigraphic detail. And careful examination of this sequence shows that the Permian fauna was not simply present one day and absent the next. Instead, the diversity of the Permian fauna declined progressively over an interval of several 100,000 years before the final pulse of extinction, a pattern consistent with a prolonged environmental deterioration driven by the early phases of the Siberian Traps eruptions before the catastrophic peak that caused the main marine extinction pulse. Life on land was being ground down over hundreds of thousands of years before it was finally overwhelmed. The February 2025 eLife study by Li Tian and colleagues adds a further dimension to this picture. The evidence from North China that some tropical riparian ecosystems recovered within approximately 2 million years does not contradict the 8 million year recovery timeline from the Karoo. Instead, it reveals that recovery was geographically heterogeneous, that the post-extinction world was not uniformly devastated and uniformly recovering, but was a mosaic of refugia and dead zones, with some environments capable of rapid ecological rebuilding and others requiring millions of years of slow species-by-species recolonization. The geography of recovery mirrored the geography of the extinction. The regions most severely affected by the kill mechanisms took longest to recover, while regions with more moderate conditions during the extinction crisis were capable of faster ecological rebuilding. This finding has important implications for understanding the kill mechanisms. The terrestrial biosphere, with its direct exposure to atmospheric change, began to feel the effects of the Siberian Traps eruptions before the marine biosphere. The destruction of the ozone layer, which would primarily have affected land organisms and shallow marine organisms exposed to UV radiation, the destabilization of climate, which would have disrupted the seasonal patterns on which terrestrial ecosystems depended, and the acid rain produced by sulfur dioxide and hydrogen chloride emissions, which would have damaged vegetation and disrupted freshwater systems. All of these would have begun to affect land organisms before the full cascade of oceanic consequences had developed. The specimen-by-specimen analysis by Jessica Whiteside of Brown University and Randall Ermis of the Natural History Museum of Utah examined nearly 8,600 fossil specimens from key Permian Triassic boundary sequences, and found that the terrestrial vertebrate fauna was reduced to an almost unimaginable degree of simplicity. From the complex Permian ecosystem with its dozens of synapsid genera occupying every ecological niche from small insectivore to large apex predator, the earliest Triassic fauna was reduced to a handful of genera, the disaster taxa that gave the name to this concept in paleontology. The most famous of these disaster taxa is Lystrosaurus, a dicynodont synapsid roughly the size of a large dog or small pig, a herbivore with a characteristic turtle-like beak and two prominent tusks, whose fossils are found in Permian Triassic boundary sequences on every continent that was part of Gondwana. Lystrosaurus had been one of many dicynodont genera in the late Permian. After the extinction, it was essentially the only large herbivore on the planet. Its fossils make up approximately 90 to 95% of all early Triassic land vertebrate specimens in some Karoo Basin sections, a dominance so complete that it speaks not to evolutionary success in any conventional sense, but to the near total elimination of every competitor, predator, and alternative. In a world emptied of almost everything else, Lystrosaurus filled every available herbivore niche simply by being the last herbivore standing. The story of Lystrosaurus deserves closer attention because it is simultaneously one of the most remarkable survival stories in the history of life, and one of the most sobering illustrations of what a post-catastrophe world actually looks like. Lystrosaurus was not, by any measure, the most impressive animal in the Permian fauna. It was not fast, not intelligent by vertebrate standards, not particularly well armed against predators. It was a stocky, barrel-bodied herbivore with a horny beak for cropping vegetation and two downward-pointing tusks, probably used in intraspecific competition and for digging up roots and tubers. Its metabolic rate and physiological flexibility appear to have been somewhat higher than most of its dicynodont relatives. Some researchers have proposed that it had a degree of endothermy, the ability to regulate its own body temperature, that gave it an advantage in surviving the extreme temperature fluctuations of the post-extinction climate. But the distribution of Lystrosaurus tells a story beyond survival. It tells a story of global uniformity. In the early Triassic of the Russian Ural region, one of the two key localities studied by Whiteside and Ermis, it is similarly dominant. In Antarctica, where Permian Triassic boundary sequences are exposed in the Transantarctic Mountains, Lystrosaurus fossils are found in sediments deposited when Antarctica was still a temperate landmass connected to the rest of Gondwana. The global ubiquity of Lystrosaurus in the early Triassic record is the fossil record's way of showing us that the disaster fauna was not just local or regional. The simplification of the terrestrial ecosystem was global. The ecological dynamics of a Lystrosaurus-dominated world were profoundly different from anything that had preceded it or that would follow it. With essentially no large predators, the Gorgonopsids were gone, the early Triassic archosaurs were mostly small. Lystrosaurus populations were regulated primarily by resource availability rather than predation. When resources were abundant, populations boomed. When resources became scarce, as they would regularly in a climate system still reeling from the extinction, populations crashed. The fossil record of the Karoo Basin shows this boom and bust cycling in the size distributions of Lystrosaurus specimens. Periods dominated by large, well-grown adults reflecting stable conditions, alternating with periods dominated by small juveniles reflecting population crashes followed by rapid reproduction as survivors attempted to rebuild. The instability was not a brief transition. It was the normal condition for the first several million years of the Triassic. The ecological consequences of this reduction in biodiversity were, as Whiteside and Ermis document, devastating in their own right. When an ecosystem loses most of its species, the food webs that remain are simplified to the point of extreme fragility. The normal ecological checks and balances, predator-prey relationships, competitive exclusion, mutualistic dependencies are all disrupted. The result is the boom and bust cycling that the new research describes. Periods of population explosion among the disaster taxa, as the few surviving species expanded into the ecological vacuums left by the dead, followed by crashes as the food web collapsed under the weight of the population boom, followed by recovery, followed by another crash. This cycle repeated for approximately 8 million years before terrestrial ecosystems stabilized into something resembling a functional multi-trophic structure. 8 million years. The entire evolutionary history of the genus Homo spans approximately 2.8 million years. The terrestrial ecosystem instability following the end Permian extinction lasted nearly 3 times as long as the entire history of human evolution. But the picture of recovery is not entirely one of prolonged suffering. The research published in eLife in February of 2025, led by Li Tian of the China University of Geosciences, examined trace fossils, plant remains, and vertebrate fossils from early Triassic sediments in North China, and found evidence that some tropical riparian ecosystems, the ecosystems found along rivers and wetlands in low-latitude regions, may have recovered much faster than previously believed. The North China data suggests that some river and wetland ecosystems had re-established multi-level food webs, including medium-sized carnivorous vertebrates, within approximately 2 million years of the extinction event, far shorter than the 7 to 10 million years that had previously been estimated for tropical land recovery. The burrowing behavior of soil-dwelling organisms, which had largely ceased during the extinction crisis and its immediate aftermath, had also resumed by this stage, indicating that the ecological engineering processes that support soil health and plant productivity had been re-established. The discrepancy between the 8 million year recovery time documented from the Karoo Basin and the 2 million year recovery documented from North China likely reflects genuine geographical variation in recovery rates. The Karoo Basin during the early Triassic was at higher latitudes and more continental, subject to more extreme climate oscillations. The North China sites were closer to the equator and adjacent to water bodies that provided local climate moderation. Geography mattered in recovery as it had mattered in survival. Organisms and ecosystems in more thermally stable, well-watered environments had better prospects for rapid recovery than those in the harsh interiors of the Pangaean continent. Among the survivors of the Great Dying, the dichotomy between the devastated and the resilient was not random. Several lineages that would go on to dominate the Mesozoic world proved surprisingly capable of weathering the end Permian catastrophe. The Archosaurs, the lineage that includes the ancestors of both dinosaurs and crocodilians, were present in the late Permian as small, relatively minor components of the vertebrate fauna. The extinction cleared the competitive landscape that had been dominated by the synapsids, and the archosaurs emerged into the early Triassic world as opportunistic survivors who found themselves in an ecosystem with abundant food resources and few competitors of comparable body size. The subsequent radiation of archosaurs, from small bipedal forms in the early Triassic to the first true dinosaurs by the Middle Triassic, was not driven by any intrinsic evolutionary superiority over the synapsids. It was driven by timing and circumstance. The archosaurs happened to have the physiological characteristics: high metabolic rates, efficient respiration, and perhaps the ability to tolerate a wider range of thermal conditions that allowed them to survive the extinction crisis at higher rates than the synapsids that had dominated before. The cynodonts, the small insectivorous synapsids that were the direct ancestors of all mammals, also survived, clinging to existence in the devastated post-extinction world. They survived not because they were numerous or ecologically dominant, but because their small body size and insectivorous diet made them less sensitive to the collapse of the large herbivore and large carnivore trophic levels. Small insectivores can persist in degraded ecosystems where large vertebrates cannot, subsisting on the invertebrate communities that recovered more rapidly than the vertebrate fauna. The cynodont survivors of the Great Dying were not the heroes of their own story. They were the bystanders who happened to be in the right ecological position when the catastrophe struck. The marine survivors followed a similar logic. The groups that survived best were those with active respiratory physiology capable of tolerating elevated CO2, those that were not dependent on calcium carbonate skeletons that dissolved in acidified water, and those that had wide geographical ranges and therefore had some populations in refugia where conditions were less extreme. The fish, with their efficient gill respiratory systems, survived at much higher rates than the sessile invertebrates. The ammonoids, free-swimming cephalopods capable of moving through the water column to find better conditions, survived, though drastically reduced, and would go on to radiate explosively in the Triassic, before being finally eliminated by the Cretaceous-Paleogene extinction. The bivalves, which had more physiological flexibility in their calcification mechanisms than the brachiopods, largely replaced the brachiopods as the dominant shelly invertebrates of the Mesozoic ocean. The ecological roles that had been filled by Paleozoic organisms were eventually occupied by Mesozoic successors, but the transition was not smooth, not rapid, and not inevitable. The world that emerged from the Great Dying after those 8 million years of ecological instability was fundamentally different from the world that had entered it. The Paleozoic marine ecosystem, dominated by sessile filter feeders like brachiopods and bryozoans, by the vast reef structures of rugose corals, by the trilobite-dominated benthos, was replaced by the modern evolutionary fauna that still characterizes the ocean today, dominated by mobile predators, bivalve filter feeders, echinoderm grazers, and the scleractinian corals whose reef-building activities we are now putting at risk through our own atmospheric carbon experiment. The terrestrial ecosystem was cleared of the synapsid fauna that had dominated for 60 million years and replaced, eventually, by the archosaur-dominated world of the Mesozoic. And it is here that the most philosophically interesting dimension of the Great Dying becomes apparent. The connection between the end Permian extinction and the subsequent history of life, including the evolution of our own species, is not merely historical background. It is causal. Without the Great Dying, there are no dinosaurs. Without the dinosaurs dominating the Mesozoic, there is no ecological pressure on the early mammals to remain small, nocturnal, and behaviorally flexible for 160 million years. Without that 160 million year period of mammalian constraint and specialization, the biological equivalent of an extended apprenticeship under extremely demanding conditions, there is no evolutionary foundation for the rapid mammalian radiation that followed the Cretaceous-Paleogene extinction 66 million years ago. Without that radiation, there are no primates. Without the primates, there is no Homo sapiens. Without Homo sapiens, you are not reading this. The causal chain is long, contingent at every link, and utterly dependent on the Great Dying having happened exactly when and how it did. A Permian extinction that was slightly less severe would have left enough of the synapsid fauna intact to competitively exclude the archosaurs from the dominant ecological roles. A slightly more severe extinction might have eliminated the cynodont lineage entirely, removing the mammalian stem group from the evolutionary tree. The actual extinction, with its actual severity and its actual pattern of winners and losers, was the specific historical event that made the Mesozoic world possible. And the Mesozoic world made us possible. This is not a comfortable observation. The Great Dying was, by any measure, the worst thing that has ever happened to the biosphere of this planet. The suffering implicit in the elimination of 96% of marine species and 78% of terrestrial vertebrate genera suffering that was distributed across billions of individual organisms over tens of thousands of years, is beyond ordinary human comprehension. There is nothing consoling about it, nothing redemptive about the specific experience of dying from anoxia in an ocean that was simultaneously too hot, too acidic, and too depleted of oxygen to support your metabolic requirements. The Great Dying was a catastrophe in the most literal and most complete sense of the word. The geological record of the Great Dying is preserved with unusual clarity in several key sections around the world, and examining what those sections actually contain, the specific fossils, the specific chemical signals, the specific physical changes in the sedimentary record, brings the abstract statistics of species loss into concrete, almost visceral focus. At Meishan in China, the site designated by international scientific agreement as the official boundary between the Permian and Triassic, the extinction fits into less than a meter of grey rock. Below the boundary at Meishan, the limestone beds are densely packed with fossil invertebrates, brachiopods, bivalves, ammonoids, gastropods, foraminifera. Above the boundary, the rock changes character, from limestone to mudstone, reflecting a change in the depositional environment as the carbonate factory of the marine ecosystem collapsed. The fossils above the boundary are few, small, and poorly diversified, the disaster fauna of the earliest Triassic. The change happens over less than a meter of rock, which at the estimated sedimentation rates of the Meishan section represents approximately 60,000 years of real time. 1 meter of grey rock in a hillside in eastern China contains the record of the worst biological catastrophe in the past 540 million years. The Karoo Basin of South Africa preserves the corresponding terrestrial record with comparable precision. The Beaufort Group sedimentary sequence of the Karoo spans the Permian-Triassic boundary in a series of reddish mudstones and sandstones deposited by ancient river systems on the Gondwana landmass. The fossils of the late Permian Beaufort Group are dominated by the Dicynodont and Gorgonopsid synapsids, the characteristic fauna of the late Permian land surface. The fossils of the earliest Triassic Beaufort Group are dominated by Lystrosaurus. Between these two fossiliferous sequences is a relatively barren interval, the fossil-poor sediments that record the extinction crisis itself, when the land fauna was in the process of collapse and the rock was not accumulating the rich fossil assemblages of either the Permian below or the Lystrosaurus zone above. The Karoo is a museum without walls. Every Gorgonopsid skull, every Lystrosaurus bone in those reddish mudstones was once an animal alive in a world we erased. The rock kept the record. We are only now learning to read it. And yet, the same event that was catastrophic for the organisms that experienced it was generative for the organisms that came after. The Triassic world that emerged from the ruins of the Permian was not better than the Permian world. It was different and, in some respects, impoverished, and for 8 million years it was deeply unstable. But it was also an open world, a world in which the competitive landscape had been cleared, in which ecological opportunities that had been locked up for 60 million years by the dominance of the synapsids were suddenly available to any lineage that could survive the transition. the archosaurs, the cynodonts, the marine groups that rebuilt the Mesozoic ocean. All of them were opportunists, inheritors of a disaster that they had not caused and from which they had escaped more by chance than by design. The new research of 2025 adds an important nuance to this picture. The finding that terrestrial recovery in some tropical regions happened within 2 million years, rather than 7 to 10 million years, suggests that life is more resilient than the darkest versions of the post-extinction picture had implied. Even in the immediate aftermath of the worst catastrophe in the history of complex animal life, some ecosystems were rebuilding functional food webs within a geological blink of an eye. The capacity of life to recolonize, to adapt, to build new ecological structures from the fragments of the old. This resilience is one of the most important findings to emerge from the increasingly detailed study of the end Permian recovery. But the resilience has limits, and the comparison with the modern world is not comfortable. The end Permian extinction was caused by the rapid release of carbon dioxide and other greenhouse gases from a geological source, the Siberian traps and the sedimentary rocks their magmas intruded. The rate comparison has been made earlier in this story. It bears repeating only in its conclusion. What took the Siberian traps hundreds of thousands of years to release, we are releasing in centuries. This does not mean that we are causing a new great dying. The kill mechanisms of the end Permian were synergistic in ways that depended on the specific starting conditions of the Permian world, the configuration of Pangaea, the chemical state of the Permian Ocean, the evolutionary history of the organisms present. The modern world is different. The organisms living today are different, with different physiological capacities. But the end Permian event is the closest geological analog we have for rapid, large-scale greenhouse gas release and its biological consequences. And what that analog shows is that the margin between a stressed biosphere and a collapsed biosphere can be crossed faster than any comfortable reading of the geological record would suggest. Stand in the Karoo Basin of South Africa on a clear morning and look at the sedimentary sequence exposed in the hillsides around you. The reddish-brown mudstones of the Permian, the ones that contain the bones of gorgonopsids and dicynodonts and the other animals of the Permian world, grade upward into the paler, more featureless sediments of the earliest Triassic. The transition is not dramatic in the way that the iridium-rich clay of the Cretaceous-Paleogene boundary is dramatic. It is subtle, gradual, recorded in the progressive disappearance of the characteristic Permian faunal elements and the appearance of the first Lystrosaurus and its few surviving companions. But if you know what you are looking at, that gradual transition is more haunting than any sudden line in the rock. It is the geological record of a world being slowly unmade, not in the geological instant of an asteroid impact, but over the course of tens of thousands of years of progressive environmental deterioration, each generation of organisms inheriting a world slightly worse than the one inherited by the generation before. The Great Dying was the worst thing that ever happened on this planet. The recovery from the Great Dying, when it finally came, was not a simple restoration of what had been lost. The organisms that rebuilt the post-extinction biosphere were not the same organisms that had been eliminated. The ecological roles were refilled, but by different players, descendants of the survivors rather than descendants of the dominants. The modern ocean, with its scleractinian coral reefs, its bivalve-dominated benthos, and its fish-dominated food webs, is not a restoration of the Paleozoic ocean. It is a replacement, built on different evolutionary foundations, operating through different ecological mechanisms, and representing a genuinely new biological chapter, rather than a return to the previous one. The scleractinian corals that build modern reefs are not the descendants of the rugose and tabulate corals that built Permian reefs. They are a separate lineage, evolved independently from non-reef-building ancestors after the extinction, cleared the ecological space for a new reef-building clade. For approximately 8 to 10 million years after the end Permian extinction, there were essentially no reefs anywhere in the ocean. The calcifying organisms that would eventually build the Triassic reefs were evolving from non-calcifying or weakly calcifying ancestors, slowly developing the ability to build the carbonate structures that characterize coral reefs. The Triassic reefs that eventually appeared were different in composition, different in structure, and different in the ecological communities they supported from the Permian reefs they replaced. This pattern, elimination of a dominant group, followed by ecological replacement by a completely different lineage, is one of the most fundamental dynamics in the history of life, revealed by the Permian-Triassic boundary. It demonstrates that there is nothing inevitable about the specific organisms that fill specific ecological roles. The brachiopod-dominated benthos of the Paleozoic ocean was replaced by a bivalve-dominated benthos, not because bivalves were intrinsically superior to brachiopods in any universal sense, but because bivalves happened to survive the end Permian extinction at higher rates. The archosaur-dominated Mesozoic land fauna replaced the synapsid-dominated Permian land fauna, not because archosaurs were intrinsically superior to synapsids, but because the specific character of the end Permian extinction happened to favor archosaur survival. Evolutionary history is contingent in exactly the way that Stephen Jay Gould described. Replay the tape of life with slightly different extinction conditions, and the Mesozoic world could have been dominated by synapsids. The mammals could have remained small for a different reason, or not at all. And the entire subsequent history of vertebrate evolution on land could have taken a completely different trajectory. The Permian-Triassic boundary is, in this sense, the hinge point of our own existence, the moment in geological time whose specific character most directly determined that the subsequent history of life would take the path that led to us. Not the Cambrian explosion, which established the body plans but not the specific lineages. Not the Cretaceous-Paleogene extinction, which ended the dinosaurs but only after the mammals had already been shaped by 160 million years of Mesozoic constraint. The Great Dying, 252 million years ago, is the event whose specific outcomes most directly determined that the world would eventually contain creatures capable of understanding what happened to it. The rocks of the Permian-Triassic boundary also preserve evidence of the physical environment during the extinction crisis that goes beyond chemistry and biology. evidence of what the Earth itself looked like as the catastrophe unfolded. The sedimentary record of the earliest Triassic, from multiple continents and multiple depositional environments, shows a consistent pattern of disrupted sedimentation, irregular bedding, evidence of unusual sediment transport events. The absence of the bioturbation structures that characterize sediments deposited in well-oxygenated water with active burrowing communities. These physical signatures in the rock reflect a world in which the normal processes of ecological engineering that stabilize sedimentary environments had been disrupted or destroyed. In many earliest Triassic sections, there is a phenomenon that geologists call the coal gap, an interval of several million years at the base of the Triassic from which coal deposits are entirely absent. Coal forms from the accumulation and burial of plant material in swampy, low-oxygen environments, and its absence in the earliest Triassic reflects the catastrophic disruption of terrestrial plant communities. The Permian had extensive coal-forming swamps, the remnants of the great Carboniferous forests that had been reduced but not eliminated during the earlier end-Carboniferous climate shift. These swamp forests, with their peat-forming vegetation, disappeared at the Permian-Triassic boundary and did not return for several million years. The earliest Triassic world was, on land, a world essentially without forests, without the complex three-dimensional habitat structure that forests provide, without the soil-building processes that forest litter enables, without the hydrological regulation that forest root systems perform. The absence of forests meant that early Triassic river systems behaved differently from their Permian predecessors and their Triassic successors. In a vegetated landscape, plant roots bind the soil and regulate the flow of water, producing the meandering river systems with stable banks and predictable flooding cycles that characterize modern and Permian fluvial environments. In the deforested earliest Triassic landscape, rivers became braided rather than meandering, wide, shallow, constantly shifting channels with unstable banks and episodic flooding that deposited coarse sand and gravel rather than the fine overbank sediments of a vegetated landscape. This braided river signature is found in early Triassic fluvial deposits on multiple continents and is one of the most consistent physical markers of the post-extinction environment. The rivers tell us that the land was bare, or nearly so, and that the ecological processes that make a landscape habitable for large vertebrates had been suspended. It was also the event that made everything that came after possible. That contradiction, catastrophe as the prerequisite for creation, is not a philosophical abstraction. It is a fact written in the rocks of the Karoo Basin and the Ural Mountains, and the Meishan section of China, readable to any scientist patient enough to count the bones and date the layers, and follow the chemical signals from Siberia to South Africa across the deep time of the Permian-Triassic boundary. We are the beneficiaries of the great dying. We owe our existence to a catastrophe we did not cause and could not have survived. And the least we can do with that knowledge is understand, as precisely and as honestly as possible, what it took to destroy a world and what it meant for those who came after that it was destroyed.